function.
What's up, guys? It's me, your boy
f
Kit
of x
again,
defined by
and
that
today
squiggly
we are
line
going to learn
right there, which
the fundamental theorem of
is
calculus,
an
part
integral,
1,
as many of you may know.
which is essentially just the
Some
area
kinds of questions you're going to get into a
asked
function
by
that have to do with an f of x defined by
part 1
that squiggly
are
line right there,
kind of like
which
these two, which is
an integral,
you'll be
as
given a
many of you may
graph
know.
like this
Um,
one.
So
And
the
then
kinds
you'll
of
have
questions you're
some
going to get
function
asked
g of x by
is equal to the integral
have to
from
do with the
0
fundamental
or
theorem
some
of
number
calculus, part
to
1
x
are
of another function.
kind of like these two,
And
which
then
is
you'll be
asked
given
like,
a
what is
graph
g of 2, and you'll have to
like
plug
this
in
one.
and then you'll have some
2
function
to
g of
x,
x,
and then you'll
is
get
equal to
asked,
the
like,
integral
what's g
from
of
0 or some number,
and you'll plug
to
in
x.
So let's
do this.
of another function.
So g of 2, and then you'll get asked like, what is g of 2, and you'll have to plug in 2 to x, and then you'll get asked like, what's g of 3, and you'll plug in 3 to x. So let's do this. So g of 2 would essentially be the integral of 2 to 0 of f of t dt. And we're pretending we don't know the antiderivative rules for this. So we're just trying to find the area under the curve. But luckily this graph, and more likely than not, you'll be given a graph where you can kind of compute based on like simple units. Like obviously this is 1 unit and this area is 2 units. So g of 2 would obviously just equal this area, which is 1, and this area, which is 2. So that would equal 3 units. And then when we're asked for g of 3, we can do g of 2, which is 3, plus the integral from 2 to 3 f of t dt, which we can say is about 1.3. So that all comes out to equal 3 plus 1.3, which is equal to 4.3 units. Pretty straightforward. All right, the next kind of question you might be asked, dealing with the fundamental theorem of calculus, part 1, is you'll be given an integral from, let's say, -2 to 2, in this case, of the square root of 4 minus x squared. And now, this should look familiar to us because it's a circle with the radius 2. So, essentially, it's just this. Here's our graph. Here's 2. Here's -2. And here's our semicircle here. And it's asking us to find the area of this. But luckily, we already know the area for a circle or a semicircle. So it's pi r squared. That's the area for a circle, so we just need to divide it by 2. And our radius is 2, so it's just pi times 4 divided by 2, which is just 2 pi, which is our final answer. 2 pi units. Don't forget your units. Alright guys, so some other questions you might be asked may look a little something like these. So this top one is asking for the area under the absolute value of x from -1 to 2. Oops, sorry about that. Now you have to keep in mind that the absolute value of x is makes any negative value of x positive. So we can't forget this little thing here. And it's just the area bounded by the x-axis. So it's just this area plus this area, which pans out to be, so this is a half, and then this is 1.5. So that area is 2. And then this is a half, so plus 0.5, which is equal to 2.5 units. So that one's pretty easy. You just have to keep the absolute value in mind. A common mistake is that some people think that because this little part of the area is in the negative x values, that the area is negative, and you have to subtract it from this, but that's false. The only time you're going to have to subtract areas is if it is below the x-axis, which we'll see in the next problem. So this one is asking us to find the area between -1 and 3 of the line 3 minus 2x. And again, it's always going to be the area bounded between the x-axis by the x-axis, unless, well, that's because it states that it's dx. If it's dy, it would be bounded by the y-axis. So we're just finding this area, which is between -1 again and 3. So that would be 3, -3. And it crosses this line at 0, 3/2. Crosses the x-axis at 0, 3/2. So here it's obvious that we have two triangles, so it's just going to be 1/2. The area is going to be 1/2 base times height of this triangle minus 1/2 base times height of that triangle, which pans out to be 1/2 times 5/2 times 5 minus 1/2 times 3/2 times 3, which is equal to 4. Now here a common mistake is, again, not to subtract this area from that area. Remember, any area underneath the x-axis is considered negative area and must be subtracted from the positive area, which in our case gets us to equal to 4 units. Remember, area in the second quadrant, which is this quadrant, but that's not underneath the x-axis, is still considered positive and doesn't need to be subtracted, unlike this one, which is underneath the x-axis. A lot of the time people confuse the two of these. For the next problem, it's asking us for the area from a -3 to 0 of this function. So we can kind of split this up into the function y equals 1 and y equals the square root of 9 minus x squared. So that function, y equals 1, is just going to kind of look like a straight line. Let's say this is -3. There. And this function, y equals the square root of 9 minus x squared, is, again, it's just going to be, a quarter circle because we're only finding the area in the second quadrant. But it's going to have a radius of 3 because, remember, this equation is going to pop up a lot on tests, and we have to remember that this is an equation for a square. So we have a radius of 3. We get our semicircle. It's more or less a semicircle. And then we can compute it. So this is going to be, it's just going to be 3 times 1. Base of 3, height of 1. And then this is going to be pi r squared divided by 4, which is just 3 plus 9 pi over 4. And that's our answer. Units. Alright guys, just a quick reminder that the fundamental theorem of calculus part 1, in order to find an exact area underneath the curve or underneath the function, this only works if kind of the area is broken up, or the function can be broken up in like triangles or semicircles or squares or rectangles and stuff like that. If you get some complicated function and have to find an area under the curve of that, which isn't breaking up into any kind of solid shapes or shapes that we know of, the only way to find an exact area is by implementing the fundamental theorem of calculus part 2, which can be checked out in one of the next videos. However, you can still if you don't know the rules of the antiderivatives yet, you can still approximate those areas by using Riemann sums from the left-hand side, the right-hand side, midpoints, or by trapezoidal regions. But we already learned that, so I'm not going to go over that. Just a quick reminder. Alright, and that kind of wraps up my video, guys. Thanks for watching. I hope I was able to help you with something. And if you want some more practice, check out my worksheet and key. Has some great practice problems on it. Alright, thanks guys. Good luck.